We all set, Cole?
Yep.
Okay, good afternoon, everyone. I'm Lloyd Dabbs from SandboxAQ. I'm the Director of Public Sector Business Development. With me is Luca Ferrara. He's the head of our MagNav QNav program for sensing for SandboxAQ. So I'll go ahead and get our slides up. Let's make sure this works. Hopefully everybody can see that okay. Okay, so again, we're SandboxAQ. We're a startup that just launched out of stealth mode on 22 March, so very recent. But we had been incubating our capabilities out of Alphabet at Sandbox for the last 6 years. That was born from a vision from Eric Schmidt and Jack Hittery, our CEO, to take a look at bringing the physics and AI together to support hard problems related to quantum. So not quantum computing, but really the near-term things that we can support from a quantum sensing, cryptography, simulation optimization, and AI, all of those different approaches that we can bring to the warfighter right now. So Eric Schmidt is our chairman of the board, former Google CEO, and then Jack Hittery is our CEO, again, running Sandbox and other initiatives for many years. So our mission is new, obviously, to the Department of Defense. But really, we're trying to bring the nexus of quantum AI to the Department of Defense right now. So from a physics perspective, that's insights and algorithms, to artificial intelligence, utilizing quantum-inspired techniques, and then on the opposite way, utilizing AI to leverage physical tools for quantum sensing. So really looking at how we can take all of those things together and help solve the U.S. Navy's challenges in the joint warfighting domain, whatever they may be. So we have three primary thrusts for SandboxAQ. I'm going to talk about one in depth today, but we can definitely follow up with any one of the three anytime based on what your needs are. First thing I'll talk about is we're focused on quantum security and communication, specifically quantum secure algorithms and cryptography, so post-quantum cryptography. We've got a whole team dedicated to supporting all of the different customer sets that need a quantum resilient architecture. We also do simulation optimization. Again, that's utilizing tensor processing units, essentially high performance computing elements to do classical and quantum simulation for the federal government or commercial sectors. And then we also do, which is what we're going to be our primary thrust of the discussion today, which is quantum sensing. So starting with your classical sensing and moving towards R&D and other types of special projects towards real, true, passive, and active quantum sensing for the commercial and federal partner space. So, We're starting with the premise that we know that we have a problem with GPS. It's one of the primary pain points for the Department of Defense, and we know that GPS loss will severely degrade the U.S. and joint warfighter dominance. We know this because it's happening right now in the Ukraine. Russia's actively jamming GPS elements within Ukraine, and we know that when we get into denied environments, loss of GPS will affect everything from UAS to our naval operations, just to forward dismounted operations as well. So we understand that we have a problem, so we need to look at how we can solve with real solutions today. So we know it's unreliable. So it's an active technique. It's intentional jamming or spoofing can throw it off. We know that. Any type of anti-satellite attacks that are main, probably active plans from China and Russia are out there. If we lose satellites, obviously it's that would be a negative for us as well. And then if there's any other interference, and there's also precision issues as well that needs a complement. So signal deflection, it doesn't have the underground capabilities, so solar time of arrival calculations. All of these things are negatives when you look at the GPS constellation. Although great, it can be complemented with some supplementary capabilities that we're going to discuss today. So we know there's a need for reliable alternatives across naval platforms. So we've had discussions with the Air Force, the Navy, across the entire DoD, and everyone says that they have real needs, but we haven't seen a lot of thrusts to solve those when GPS is at risk, or when it's limited, or when you have autonomous needs. For example, a drone that potentially doesn't have a GPS connection and has to return home. So these are all areas that we're looking at to really understand the Navy's needs for alternatives to GPS and precision navigation and timing. So the goal here is to, and which is our main thrust right now for our quantum sensing team, is to build an alternative to GPS utilizing that Earth's magnetic field as a complementary signal. So we've got a generalized map of the Earth from a magnetic perspective. Our intent is to take specific platforms and really refine that magnetic understanding of individual areas to give you better positional navigation and timing in real time. And I'll turn it over to Luca to speak more about the approach.
Thanks, Lloyd. Yeah, so as Lloyd was mentioning, the idea behind magnetic anomaly-based navigation is to provide one more tool set that's globally available, is resistant to jamming and spoofing, is all-weather, and can assist in situations in which we need that absolute position reference and GPS is denied, or if you're operating underwater, it's just simply unavailable. So the way that we envision this working and the way that we've approached this is to use magnetic anomaly-based navigation as an input into a sensor fusion system where you're essentially trying to boost your capability to do inertial navigation by providing yourself an ability to anchor yourself to a true location should the signal of interest become unique enough, and also on a longer time horizon, use the local variations in the magnetic field to constrain your drift and essentially extend the amount of time that you can operate without GNSS. And so this essentially is conducive to current techniques of sensor fusion, where you might use things like vision or celestial navigation, but provides a different modality that is uncorrelated in some important regards to the other ways of doing alt-PNT. And I think we all probably believe that we need a variety of solutions to really have something robust. Next slide, please. So what does that look like? This is just a representation of showing you that an inertial system is basically taking some kind of time frame and using accelerometers and gyroscopes. Even if they are extremely good grade, navigation grade, they will ultimately compound errors until the location solution is no longer really useful. And if you don't get an absolute fix, regardless, depending on how you do that, you will have that compounding error. The qualitative difference with a technique like magnetic anomaly-based navigation is that you do have the ability to anchor yourself. And so you're not necessarily doomed to have your location accuracy be worse in 1 hour than it was right now. It could actually be better. And so that's kind of qualitatively very different than inertial or dead reckoning type of techniques of navigation. So this isn't, I think magnetic anomaly-based navigation in and of itself is something that can be, has been demonstrated to certain degrees as being feasible if you have your magnetometer towed about 2 to 3 ship lengths behind the vessel itself. Most ships are made of ferromagnetic material, so they're going to have quite a big impact on the electromagnetic spectrum. So getting that sensor towed behind gets it nice and clean, gives you a clean signal you can do map matching with, and there's good evidence to believe that a robust system like this would give you very good location accuracy. The challenge that is a software and hardware challenge is getting to that green spot on the vessel where you can actually have this device denoise for the vessel's electromagnetic interference and still give you, in the end, what the true value is in that point in space that you should be doing the map matching with. And that's an engineering challenge. And we believe that there's techniques that apply to other domains that show promise for that. So what are those other domains that we've been working on? This is a representation of the challenges we've been focused on. They're kind of fourfold. And this is just to give you an idea of the trade space of how we think about the MagNav problem. What I described to you before is the calibration problem. And that's the idea that you need a clean input signal into that process to get a good output. And the goal is to get a good output to give you a location solution that's workable. That's right. But it's contingent on things like the map quality. We believe that the map quality today is good enough for certain use cases, but will need to be improved in the future to allow other use cases. And there are ways to improve the map with different degrees of scalability that we think could be explored further and could even be done synthetically using things like image-based machine learning or techniques used in other domains like image processing. But that's an area of further research. There's the challenge of integrating this. We view this as being, integration is not something to take lightly in terms of it being a challenge, but what we want to make sure we are doing is bringing value to any type of solution so that MagNav improves in a measurable way your location accuracy in the sensor fusion approach. So it is just that we can make it a tool set that when you think about all the different ways you want to complement GPS, that it's adding value, and we believe there's a path to that. One of the challenges, of course, is generalizing these techniques. So you can make a model that's based off of one aircraft and can work quite well, but then how do you make sure that that model only needs to be trained once and can work on every other aircraft? And this is where AI is really critical. Getting the data sets to use machine learning techniques to understand how to calibrate that sensor for a given platform, and using AI to understand that potentially different models make sense at different points in time. And so this is kind of where we see the intersection of AI and physics here. And so we fundamentally believe that this is an AI ML problem, and that more data, better quality data, better simulation techniques will improve really all these things. Next slide. So just to give you a sense of what we've been able to demonstrate already, this is using public data that was published by the Joint AI Accelerator at MIT from the Air Force. They published a data set where an aircraft, survey aircraft, had several magnetometers on it. It flew around in Canada, I think near Ontario, and it essentially gathered data with one key thing. It was gathering data with a magnetometer that was extended behind the fuselage on a boom, kind of analogous to towing a magnetometer behind an aircraft, a ship. That was used as the clean signal for the training of this data. So extending a magnetometer about 12 feet behind the fuselage of the aircraft was clean enough to be considered the truth. And the challenge posed to the AI ML community was, can you use the sensors that are on the aircraft that are noisy to predict what that clean sensor that was behind the aircraft should be saying at that point in time, treating it as the truth? And what we were able to do is show that machine learning techniques outperformed classic techniques, one of which is called Toles-Lawson, and basically is a linear approach. So we showed that you can use neural networks, AI/ML, to learn these relationships and do better. What we also did is fuse that information into a sensor fusion algorithm, a flavor of a Kalman filter that essentially constrained the drift in the method I was describing before. This is real data though, and what you can see in the 30-minute mark is that we've anchored ourselves to our true location, because the signal and the flight path is on the right. The signal in that area was unique enough to actually give the Kalman filter high level of confidence in its absolute lat-long location along that flight line. At the end, you can see you've got about 100 meters of error between where you are and where you truly are. But if you had relied on only inertial systems, you'd be at 400 meters. Next slide, please. What you're seeing here is the next step we took. We worked with the US Air Force. A paper was published to IEEE where some F-16 flights were done. This, we extended what we had learned to apply different neural network techniques with a much noisier data set and still achieve results where we got about accurate to 1 second of travel on an F-16 in a 10 times noisier environment, which was very promising. And we're continuing and extending on that research today.
So where do we go from here? We've had, I think, a lot of good discussions and partnerships with the Air Force Institute of Technology, as Luca mentioned, with the AI MIT Accelerator. Air Combat Command is very interested in this capability and what we've been maturing thus far. So we see a lot of good opportunities to bridge that gap between classical magnetic navigation in the near term, and then focus on research opportunities for quantum navigation for the long term. So that means data, that means expertise, really understanding the Navy's problems so that we can very quickly prototype solutions and get it out to the warfighter, because there's going to be a lot of companies out there, at least within the quantum domain, that are going to be selling vaporware. We're not one of those. we're actually here to solve these problems as quickly as possible and try to iterate it over the next several years to give you a solution. So that's everything that Luca talked about, from map quality to sensor calibration to integration across platforms, and then just that platform generalization that we are talking about. All of those areas that we consider challenges are areas that are actively within our roadmap from a sensing perspective over the next 5 years. So what does a framework look like working with the Navy? I think there's a lot of opportunity to look at sensing, not just from an alternative to GPS, but you can also do penetration underwater as well for detection. But from a MagNav perspective, we think that we can get more access to data that will help us better refine our approach to quantum navigation. That's access to the payloads, flight testing, and then the integration of the AI models to support what the Navy needs right now on their most critical platforms for specific domains. Doing those performance evaluations and then working on the magnetic map improvement process. So then when we do get into a denied or contested environment, the GPS has an alternative and a supplement that works in tandem with its basic framework. So those test flights are very critical, and I think finding the right partner and sponsors within the U.S. Navy, whether it's ONR or any type of SOF-related elements, or anyone just in general that really understands the need for positional alternatives. I think we're a company that provides a solution within the next 12 months to help you get where you need to be from a prototype perspective, and then work towards with those long lead industrial integrators to get those right solutions onto your platforms right away. So with that said, we are ready to work with the U.S. Navy. We're excited to work with the U.S. Navy. Our federal team is mostly ex-military, but we have that feel from quantum, or from Sandbox Quantum, and the Sandbox team, the expertise there, we all brought over with us. So we're very excited to, I think, work with the federal government in that regard, and hopefully the Navy reaches out to us to discuss this further. That's our contact information, and you can also look at our website right there as well if you want to find out more. But feel free to reach out and set up a discussion if you'd like to chat further. I'm going to stop sharing to see if there's any questions. Okay, with that said, we appreciate your time, and we look forward to the next steps for anyone that wants to look at real solutions for PNT. Thank you.
Thank you very much, guys. And thank you everyone in the audience for tuning in, and we will take a 5-minute break and move on to the next presentation. Thank you all.
Thank you.